This is the video where everything starts to come together. We're going to derive the rule for what happens when you take the Laplace transform of a derivative. This is the step that allows us to use Laplace transforms to turn a differential equation into a much easier algebraic equation. By the end of this video, you'll be able to take a differential equation and turn it into an algebraic equation in S. We won't finish solving it. That comes in the next video, but you'll see exactly how the transformation works. When we use Laplace transforms to solve a second-order ordinary differential equation, we need to be able to find the Laplace transform of a first derivative and a second derivative. To find those transforms, we're going to use the definition of the Laplace transform. This definition tells us that we can find the Laplace transform of a function by taking that function, multiplying it by e to the minus st, and then integrating from 0 to infinity. This gives us an algebraic function in terms of S. Let's first use this definition to find the Laplace transform of a first derivative f prime of t. Our definition tells us that this Laplace transform is going to be the integral from 0 to infinity. We have e to the minus st, and we multiply that by f prime of t and integrate with respect to t. We're going to need to use integration by parts to solve this integral, because that will reduce this integral to an integral with just e to the minus st times f of t instead of f prime of t. I'm going to start by writing down the formula for integration by parts. It's the integral of u dv, and it's equal to uv minus the integral of v du. We're going to let u be e to the minus st, and then dv is going to equal f prime of t dt. So when we integrate that, the derivative is going to go away. Du is equal to minus s e to the minus st dt, and then v is just f of t. Let's now apply our formula. We have u times v. That gives us e to the minus st times f of t. And we're going to evaluate that from t is equal to 0 to infinity. And then we subtract off the integral of minus s e to the minus st f of t dt. And that integration goes from 0 to infinity. Let's now simplify this. If we first apply the upper limit of integration, we have e to the minus s times infinity times f of infinity minus e to the minus s times 0 times f of 0. And then in this next integral, we have two negatives, so that becomes a positive. We can bring the s out in front, and we have the integral from 0 to infinity, e to the minus st times f of t dt. E to the minus infinity is going to go to 0, and here's what we get. We end up with minus f at 0, because e to the 0 is 1, and then we have plus s. Now we need to recognize something. This integral right here is just f of s. That's using our definition of a Laplace transform. So let's go ahead and let's put this in. We have plus s times f of s. Now we're going to rewrite this into the more standard form. This is equal to s times capital F of s minus little f at 0. That's the Laplace transform of the first derivative of a function. Notice that this is an algebraic expression in terms of s, and the initial value, little f of 0, appears automatically. Now let's walk through how to find the Laplace transform of a second derivative. This is going to be really similar to what we just did. We're going to start with the definition, and this is equal to the integral from 0 to infinity, e to the minus st. Now we have f double prime of t times dt. We again are going to use integration by parts, so let's put down the formula. We have the integral of u dv is equal to uv minus the integral v du. Just like with the first derivative, our u is going to be e to the minus st, and then our dv is what's left, and that is f double prime of t dt. Our du is minus s e to the minus st times dt, and v is just f prime of t. This gives us u times v, so this is e to the minus st times f prime of t, and this is evaluated from t is equal to 0 to infinity. And then we have minus a negative, so let's go ahead and make that positive, and we'll pull out the s, so we have a plus s, the integral from 0 to infinity, e to the minus st, f prime of t dt. Just like with the first derivative, our upper limit of integration is going to give us e to the minus s times infinity, f prime of infinity, minus e to the 0, which is just 1, times f prime of 0. And then we have plus s. And let's look at this integral right here. This integral is what we just evaluated up above. Let me go show you that. It's this integral right here, and we came up with that solution. So that's what we're going to substitute in. S times capital F of s minus little f of 0. This is s capital F of s minus little f of 0. This term is going to go to 0, so we're just left with minus f prime at 0 plus s squared capital F of s minus s little f of 0. And we're going to write this as s squared capital F of s minus s little f of 0 minus little f prime of 0. And there's the formula for the Laplace transform of our second derivative. It's an algebraic equation in terms of s, and it contains the initial conditions. Here's the key idea. When we take the Laplace transform of an ordinary differential equation, it becomes an algebraic equation in S. To make things easier, I've written down the derivative formulas that you'll use the most here in this green box. The initial conditions are built into the derivatives when we take the Laplace transform. This means that we don't have to solve for C1 and C2 at the very end. It's already done. Let's now walk through an example so that you can see how you can use Laplace transforms to transform an ODE into an algebraic equation in S. We're going to take the Laplace transform of the equation y double prime plus 3y prime plus 2y is equal to 0 with the initial conditions that y of 0 is equal to 1 and y prime of 0 is equal to 0. Let me back this down here a little bit because we are going to need to use those formulas. Y double prime becomes s squared capital Y of s minus s little y of 0 minus little y prime of 0. And then we have plus 3 times y prime. Y prime becomes s times capital Y of s minus little y of 0. And then we have plus 2y. That is now capital Y of s because we just took the transform. And this is equal to 0. Now we're going to substitute in our initial conditions. We have a y of 0, a y prime of 0, and another y of 0. This gives us s squared, capital Y of s, minus s times little y of 0, that is equal to 1, minus y prime of 0, that's 0. And then we have distributing the 3s capital Y of s, minus 3 times little y of 0, which is equal to 1, plus 2 capital Y of s is equal to 0. Now we're going to combine all the y of s terms. This gives us s squared plus 3s plus 2 times capital Y of s. And let's go ahead and let's put everything else on the other side. This gives us an s plus 3. Now we'll solve for y of s, and we get the solution y of s is equal to s plus 3, all divided by s squared plus 3s plus 2. This algebraic expression is the Laplace transform of our differential equation. The next step is to use what's called an inverse Laplace transform to find little y of t, which is the solution to the differential equation. In the next video in this series, we're going to learn exactly how to do that. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.